Right, good afternoon, everybody. Thanks for coming. So today I'm going to talk about a little bit of research I've been doing on mixing batch and real-time using Cassandra and Shark. So just to begin with a tiny bit about me. So currently I'm the analytics tech lead at SwiftKey. So SwiftKey, we make the #1 selling Android app, which is a keyboard. We do various other things as well. And I deal with the analytics infrastructure. I also do a bit of Cassandra freelance stuff. You may see me write blog posts or answer questions on the mailing list or various other things. And today's talk fits under the freelance Cassandra banner. This isn't some work at SwiftKey. This is some work I've done in my spare time. And before I did Cassandra and analytics development at Akunu. So what am I going to talk about today? So yeah, the subject is batch analytics and real time. So I'm going to sort of work through a particular use case that I have in mind for this. And I feel that this use case is kind of in between the tools that are available, and you can't quite do it today. So I'm sort of doing it. I came up with an idea, and I'm trying to show that it does something useful. So I'm going to explain what my idea is, explain what Spark and Shark are, and I've even done a bit of performance testing to show how it works. So what do I mean by batch analytics and real-time databases? So if you're using something like Cassandra, you probably have some real-time requirements. You want to, power your website or power your stock picking system or something where you care about how quickly you get answers back. If you don't care about that speed, then you probably shouldn't be using Cassandra because it's doing extra work that you don't need. But whenever you have a database, there are always queries to do on it which are slow or you didn't think of in advance or that you didn't even know you could possibly do, but someone else will come and say, can you run this query for me, please? So if you're running a real-time system, you'll say, no, you can't do this because if you run this query, then our performance is going to tank. Requests are going to time out, customers are going to complain, stuff's going to break. So you say, no, I can't do it. But this query may be immensely valuable. It may be, the difference between, it may affect a marketing campaign, for example, that may make loads more sales. It could be a really valuable thing. So they won't take no for an answer. But then you think, well, actually, maybe I can't even do this query. Cassandra doesn't support every query. It doesn't support a lot of queries, actually. You can't issue a query which is going to scan through all of your data and find something else. MySQL or most SQL databases could do that, but they will hurt your performance. But yeah, Cassandra doesn't even support a lot of these queries. So what do you do? So let's think of a concrete example. I always prefer to think of concrete things. So let's say we've got a user accounts database. This is a list of fairly boring user accounts, but every operation that your website does hits this, at least to verify someone's password. So this sort of underpins your entire website. So if you have timeouts or latency spikes here, then everything slows down. Page load slows down, things time out, people get unhappy, and maybe stop using your site. So you do care about the latency quite a lot here. You don't just have user accounts; you have other stuff. Maybe you're doing messaging or whatever. You've got other things in your database, in your Cassandra database even that are ongoing. So you've got this balance of these reads. You've got some writes in some other column families. You've got all this stuff going on in Cassandra. But let's carry on focusing on these user accounts. So let's say you've got this schema, you've got some user ID, bit of stuff about the user. Actually, the stuff that I'm going to focus on for this example is the country and the last visited. So country is just there, just remember that. Last visited is the only thing in this table which isn't static. Pretty much, maybe you can change your username, maybe you can change your email or your password, but that doesn't change very often. Last visited will change every time you hit the website, so that's the thing that varies. That's what it looks like if you run it in CQLSH. I've randomly generated some stuff for performance tests, so I'll use some data that looks a bit like that. Okay, so you've deployed this system, your accounts database. It's working great. You've moved on to another project. You just have to make sure it's working, check it out yourself and perform Cassandra upgrades. But you leave it alone, it works. You mind your own business, and then someone from marketing walks in, and they ask you a very important question. Please, can you find all users from Brazil who haven't logged in since July, and their email is @yahoo.com, and I need the answer on Monday. So, you can imagine they're going to launch some advertising campaign on Yahoo in Brazil to say, please come back to our site, it's great. But they want to know who it is so they can say to Yahoo, please put these adverts up. So, it's pretty important that you get this right, because otherwise they're going to waste all this advertising money, and maybe you won't get any of your users from Brazil to come back. But it's also, you don't have to do it particularly quickly. It's Thursday today, you could run the query tomorrow, and then it could run over the weekend, you get the answers on Monday morning. So a few sort of thoughts about this query. We've got 500,000 users from Brazil. I just picked that number. That's how many users we have. So that's 60 megabytes of raw data, something like that for our accounts database. So it's not a huge amount of data, but how do we get that data? So we didn't put index on country. I didn't show you any indexes there. There's no way of selecting by country. Note also that most of this data is unchanging. The timestamp is changing. That's the only thing that is, and that we do actually care about that for our query, because we're saying people who haven't come since July. But if we miss people who haven't been since July but came in the last hour, maybe we don't care too much. So basically, we could work on a snapshot of the data, or the data from yesterday maybe would work as well. It doesn't have to be the totally current data. Yeah, we can take hours running this query. That doesn't matter. I guess we could take the weekend to run it, but it would be nice if you had the result before you went to the pub tomorrow evening. So if it took hours, you'd be happier. And note also that we probably won't have to rerun this query again. Maybe we'll have to run something related to that, but we don't have any knowledge of that. So we don't really want to build some complicated system or add an index or things like that may require maintenance in the future, because we probably only have to run this once. So before I explain more technical stuff, just why am I interested in this? Why do I want to do this? Well, I think this sort of use case is a bit underrepresented in the tools that are available, and I have seen people spend days writing code, messing around with databases to answer stuff like this. So if there are tools there, then it would help. So I thought, let's see what we can do. So what can you do? What can you download off and run? So you've got Cassandra. Well, you can run Hive on Cassandra. So we've seen talks today where people have been running Hadoop jobs on Cassandra. Well, you can stick Hive on that, and it will read data out of Cassandra. You can run arbitrary SQL queries. That will work, but it may cause you some problems. So you're going to compete with Cassandra on all of the resources, and you don't know what Hive's going to do. It's going to run a few map-reduced jobs. Some will be I/O intensive. Some will use lots of memory. Some will use lots of CPU at various different times, and you'll probably find your latency will go through the roof, and you'll get some timeouts, and people will complain. You may find that because you're reading data through the Cassandra query interface, Hive is just another thing that's querying Cassandra. You may get some extra GC pressure on Cassandra, which again hurts your latency. And you may also find that you flush your cache, you pollute your cache so that your hot set of user accounts is no longer in cache. So let's not do that. We could write some code. We could extract the data, set up a MySQL instance or something. It's only 60 megs of data to extract. We could write some code to read through it and do that. That's not very good. We're going to have to write some code. We'll probably get it wrong. It will be single-threaded, which means it will be slow, so it probably won't impact our cluster too much, but it may take a very long time because it's just one thread reading through your data. And if that fails after 10 hours, then how do you restart it? Things like that. And you've still got the caching problem, although because it's so slow, that may not matter. So we don't really want to do that. We could also clone the cluster. We could say, right, we've got this Cassandra cluster here. Let's copy the SS tables off disk into another one, and then we can do what the hell we like there because it's not powering our system. But that's going to generate the worst possible network load. It's going to copy all your data out, and it's a manual import. So I mean, I said that we're not going to run this query again, but maybe we're going to want to run some different kind of query next week. So if every time we had to run a query, we had to copy all of the data out of the cluster, that's not an incremental thing. So it's pretty difficult to do. The final thing is quite a common way of solving this problem is to add a sort of logical data center, which you don't read and write from in your real-time application, but you run your Hadoop or Hive jobs on, which does work well. But for us, that's not great because we'd have to bring a new data center online before Monday, which again involves copying all the data out. And yeah, we need to get some more hardware. Maybe we're on the cloud, so that's okay. But if we're not, then we're probably not going to get some more boxes by Monday. And keeping this extra cluster maintained, well, if it's really busy running your query, then it's still going to drop writes and get out of sync. Maybe that's okay, maybe that isn't. I don't know. So this is a reasonable solution to this problem in some cases, but when you're doing sort of the occasional high value ad hoc query, it's probably not the right thing. So let's talk about Spark and Shark, the two tools that I'm going to try and use to solve this problem. I couldn't find a Shark logo, but Shark is Hive on Spark. That's where the H comes from, I think. So Spark, so it was developed by AmpLab in Berkeley. It's a distributed computation tool. It's a bit like Hadoop, so you can replace Hadoop with Spark. But the main reason to me why it's interesting is it's designed for iterative algorithms. By iterative, I mean that make multiple passes through the data. So most SQL queries you do actually have to read through the data more than once, and this is just like a simple filter. You end up reading through data again and again. That's really bad for Hadoop because it has to write it out to HDFS, replicate it, and then read it back in again for the next job. So you're doing a lot of I/O and network for every job. But what Spark is designed for is to store, rather than the intermediate data, it stores the intermediate computation. How do you get from one step to another? So that if something fails in between, you can rebuild it from just by applying the computations to that little bit of data rather than pulling it back in. Which means that you can store this in memory. Like almost all queries you do, the amount of data rapidly decreases with each iteration. So in our case, we're reading through all of our data to extract 60 megs. So we can obviously store that in memory, distributed or not. So that's a pretty nice feature. So you find that once you've done your first pass through the data, Hive queries on Spark will run many times faster than Hive. People have reported more than 100 times speed improvement. So Spark is used by many people. I just picked a few off their website that you've probably heard of. So it's fairly new, but it is being used in production. So Shark, this is Hive on Spark. It looks like Hive. It's the same query language. You can use the same user-defined functions. You can use the same storage handlers, the thing that pull data out of other systems into Hive. So yeah, it looks pretty much the same to you. But a really nice feature of it is that you can cache tables. So you can write something like this: create table user accounts _ cached. That's giving Shark the hint that it needs to cache this as select star from user accounts where country equals Brazil. So if you ran that query, what it would do is it would read through all of your data, only keeping the data from Brazil, store it in memory across your nodes, and then you can run really complicated queries on it ridiculously quickly. It will read through 100,000 records a second per core kind of speed once you've got it in memory like that. So you can't do that in Hive on Hadoop at all. So I think that's kind of the killer feature of Spark for me. It means that if you're an analyst, you can come in the morning, you can run this cache, go away and have some meetings and make some coffee or whatever, and then you come back at lunchtime and everything's in memory. And now you can do interactive queries on your data set. that's the thing you care about there. You don't care that it takes hours to start, but now you're sitting at your desk. You don't want to have to wait hours for each query to run. Now each query runs really quickly. So now we get to Shark on Cassandra. So you can do this now. There's the CQL storage handler, which you can download. It's not part of Cassandra yet. There's a ticket to sort of integrate it, but you can find it on GitHub. I don't think it's properly released yet. There's probably a few bugs in it, but it works pretty well. And actually, there was a talk at Cassandra San Francisco, if you were there, about using this. And Uyala, they do use it, and they presented some great performance results there of it working. But it does suffer from the problems I highlighted before with running any Hadoop job on Cassandra. So I have written, I guess they're sort of somewhere between a prototype and an alpha of SS table storage handler, I'm calling it. So what this does is you run Spark nodes on your Cassandra nodes, but instead of pulling the data through the Cassandra CQL interface, you pull it through the raw SS tables on disk. So there's various advantages to that. You have a bit more control over the I/O that's going on, so you can have less impact. You're not going through Cassandra, so there's no GC problems inside Cassandra because you're not touching the Cassandra JVM. And you can also say, don't cache any of this data, so there's not going to be any cache pollution. So just some diagrams to show how that works. So this is what happens if you run Shark through the CQL storage handler. You've got disk, memory, Cassandra. Then you've got your two processes. You've got your Spark worker that's doing your Hive query, and you've got this is your client, your website that's doing the things you really care about. And then maybe you find you get some latency spikes. So what the SS tables storage handler does is it skips straight from SS tables on disk to the Spark worker. So we skip the cache and we skip the Cassandra JVM. There are a few disadvantages of this, which I should say before I show you it working. So we can't do any reads from other nodes to find out if we've got the latest value or not. We just read the file and take it that that's the latest value. So that's equivalent to the CQL storage handler reading at consistency level 1. It just reads from one node. That's not too bad. I mean, especially for the query that I'm thinking of here, where most of this data hasn't changed for 2 months. So it's almost certainly going to be consistent across all of your nodes. This second point, always runs task like all the data, is actually mostly an advantage, but it's a disadvantage in some cases because you don't have the option of running non-local tasks. So maybe one node is running slow because its CPU is doing something. You can't sort of allocate that task to another node because we can't copy that data across. We don't have HTFS or anything to do that for us. Maybe the biggest disadvantage of this is that we're not reading any data in the mem tables. We're only reading files on disk. So if your data hasn't been flushed yet, then it won't appear in your query. You could work around that if you wanted to. You'd probably have to hack Cassandra to add it. But at least for my example, this doesn't matter too much. But you could solve that. So let's have a look at some performance results to see if it actually works. So I set up a 4-node Cassandra cluster on EC2 using M1 large instances. These have 2 virtual cores, 7.5 gigs memory, and 2 ephemeral disks. I was using the local storage on them. So you need 1 Spark master. That's a little bit like the job tracker in Hadoop, if you're familiar with Hadoop. I set up the Spark workers on the 4 Cassandra nodes. And I limited each worker process to only use 1 core and 1 gig of RAM. So you can tell Spark, you're only allowed to use these resources on these nodes. And what I wanted to do was compare the CQL storage handler with the SS table storage handler. So I've got some results from that. Just a little bit of stuff on the configuration. So I'm using the latest version of Cassandra 1.2, 3 gig heap. So that's almost half my memory is on the heap in Cassandra. I'm using virtual nodes, replication factor 3. I've got 4 nodes, replication factor 3, because my user accounts care about consistency, let's say. And I generated 100 million random users. I wrote some Python code and piped it into JSON to SS table to generate some data. But apart from this, I didn't do any optimization or tuning. Let's say that the person who deployed this, they just set it up and they didn't want to be bothered with any tuning. Few tools in case you're interested. So I used the metrics library from CodaHail, and well, I think it originally came from Yammer. It's absolutely fantastic, really good for instrumenting your code to get some results. So a good tool to use. So I actually used that to pipe the results through to Ganglia, so I could see what was going on as I was running the tests. I wrote some load generators using the DataStax Java driver. And Google Spreadsheet is a surprisingly useful tool, especially for looking at time series data. It's got this really nice visualization where you can zoom in on different times, which I didn't realize existed. So that's a good tool. Okay, so let's look at the first test I ran. So this is Cassandra idle. Cassandra's not doing anything at all, just a sort of baseline. And the query I'm actually going to measure is this caching query, the one I said before. Read through all the data, filter out only the ones from Brazil, and store it in memory. So this took 33 minutes through CQL storage handler and 13 minutes through the SS table storage handler, which equates to about 130,000 records a second. So this is about 2.5 times faster. And in fact, this is slightly unfair on the SS table storage handler because the CQL, we can't actually limit it to one CPU because it's talking to Cassandra. Cassandra's using some CPU. It turns out that if you only give it one CPU, it doesn't use much more than one, but it uses about 60% rather than 50%. So that's a little bit unfair, but it doesn't matter. So it's faster, right? But you'd expect it to be faster because we're not serializing, deserializing, shifting stuff over the network and other things. So now we've done that, let's just show that we can actually run the query we want to run. So we've got the data in cache, so we can run our query. So this is the Shark query or the Hive query. The only thing that looks a bit weird is the email. I randomly generated emails. I didn't have the yahoo.com, but that one gives a reasonable amount of data. So this is the query you can run, and it took 18 seconds, right? That's the really nice thing. So this read through, the 500,000 records. Actually, the randomly generated one turned out to be 400,000, but a reasonable number of records, and the answer was 282. If you care. So you can run your result really fast now. Okay, so this is kind of the baseline thing, but actually we don't have an idle Cassandra. We have lots of people visiting our website. So I added a read load of 200 reads per second, but remember when we actually log into our website, we're updating the last visited time. So actually what I'm doing is I'm reading in the user account, and then I'm writing out the last visited time saying, yep, I've just come. So I'm measuring the latency of that process, because that's the thing I really care about. If this latency is high, then my users are going to time out and get unhappy. So for the test, I ran the CQL storage handler, and then worked out how long it took, and then rate limited the SS table storage handler to that speed to compare the latencies. So, I mean, you could run it slower and the latency impact would be lower, but, to get the comparison, let's run them both at the same speed and see what happens. And this is what happens. So the different lines here, so the yellow is the mean latency for SS tables, and the green is the 95th percentile latency for SS tables, and then the blue and the red are the same for CQL. So you can see the mean latency is lower, but probably more interesting is the 95th percentile is much more consistent. So there's those two big spikes when reading through the CQL loader, but there's two much smaller spikes otherwise. So just for comparison, when you're not running a query, the mean latency is about 20 milliseconds, and the 95th percentile is about 60. So we do have an impact on latency. Of course we do. We're using some I/O. We're doing 200 random reads a second across our cluster of 4 nodes. So we're using a reasonable amount of our I/O, but now we're running a query on it. So we are going to have some impact. The question is how much and how predictable. So so this shows the latency impact is less on the for the mean latency, but the 95th percentile latency, the peaks are much lower. It's much more predictable. So I think that's a sort of more interesting result here. But yeah, we still have some latency increase. So as to why this happens, well, I didn't spend too much time looking at it, but I expect the average latency changes because we're using one core out of two. There's just less cores available to do your stuff. And maybe the CQL storage handler has some of those latency spikes, do some GC because there's lots of data going through the CQL interface. I don't know. I didn't measure it, so I don't know what was happening there. So the final result was trying to say, well, okay, we've got some other tables on our Cassandra cluster doing loads of inserts. What happens there? But I'm still measuring the read latency. You normally care more about read latency than write latency. So I added 2,500 random inserts a second into another table, and I got this horrible graph. So this doesn't really show anything useful. So it's like, so just to explain what this is showing. So the beginning is just the load, the read load, and the write load. Then add the CQL query. I didn't actually let it complete, just ran for half an hour, then I killed it, left it for a bit, then run the SS table 1. And there's loads of latency spikes even when I'm not running any queries. So this is basically showing my insert load is harming my read load. So I guess it's showing my cluster isn't really big enough to do what I'm trying to give it. It was quite late at night by this point, so I didn't run any more queries. But if I had more time, what I would have done is run it with a bit less insert load to try and get a flat latency without any queries, and then maybe we'd get some interesting comparison there. But I didn't have time to do that, so this doesn't really show anything particularly useful. Yeah, lots of latency there is anyway. So what do we find from the performance? So it's 2.5 times faster, which means we're using less resources to do the same thing, which is always a plus, but that's not the main excitement. The main excitement is that the latencies are more predictable when running at the same speed. So it shows that this approach of bypassing Cassandra to read the data does work. Actually, what you'd probably want to do though is limit it further. Those latency spikes may still be too much, so you'd actually run it even slower than that. So I guess if you were going to run this on your website, you'd probably have a graph of speed you can run it at versus latency impacts. You can say, okay, so today I need to get the answer in this time. Oh, right, I'm going to have this latency impact. Is that okay? Yes. If it's not, then you run it a bit slower. So I guess if I had this, what I would do is I'd run it. I'd work out. So I need the result by Monday. Actually, I'd prefer to have it Friday evening. Let's kick it off now. Estimate it's going to take 24 hours to run. Work out that speed, which will be really slow. It'll be like 100K a second or something. Rate limit it to that, and then you'd expect to have very, very little latency impact. Okay, summary. Time is almost up. So I spoke about a use case which I don't think is particularly well served by current tools. Spark and Shark, what do they do? And then, the thing I've written, SS table storage handler with some results. Finally, what am I going to do with this? Well, it needs a name. If you have any suggestions, please tell me. I need to push it to GitHub so people can use it. But yeah, if you're interested, then please come and talk. It's just a research project that I've done. If you want to use it, if you think it could do something or couldn't do something, then please let me know. Thanks very much. Do you have any questions? Yep.
I was just in the internals hole, and have you just taken the DB layer? Have you taken the existing code, which is reading the SS tables, and then just put a DB layer on top, or have you kind of?
Yeah, so I'm using the, there's a merged iterator you can do that merges all your SS tables together and gives you the rows in order. So I'm using that. So I've written very little code to do this.
So it feels like the main thing that you want to be optimizing for in this case is to minimize impact on latency. And I guess one of the things that you did do was you had this where clause in your query, which was bringing the data into memory. might be interesting, I was thinking, to have a continual process where you can bound I guess the sort of out of dateness, what's the word I'm looking for? You can bound the staleness of the data at a certain rate and just get everything into an in-memory state, and then ask that query or any other query, and just have that running continually in the background.
Well, that's to get the data that, for people who haven't logged in for a long time, you mean, because that's old data.
Right, okay. Oh, I see, yeah.
I mean, yeah, I guess, I mean, particularly in this case, yeah, because I'm looking at old data, so I could just look at old SS tables, I suppose. Sorry, is that?
It depends on the boundary query. Is
It
the
depends.
in-memory representation compressed?
The in-memory representation is no, I don't think it's compressed. It's basically a object array, so it's very efficient in Java to iterate over, but I don't think it's compressed. Yep.
Did you have to do anything with Mesos or Yarn?
No, so I didn't set up Mesos or Yarn. You can use Spark without Mesos or Yarn if you've only got one job. So my one job is my Shark client. But then what it does is it just grabs all the resources, and if you try and run another one, it just waits until you finish. Whereas if you have Mesos or Yarn, then it will say, oh, you're not using this at the moment, someone else can use it, and would like schedule between them. So I didn't set up Mesos or Yarn for this, but it wouldn't have made any difference because I only had one client. Asghar.
You have to bring that node down because if you're running your tool when Cassandra is already running, then what happens? Parallel compactions, all these things is completely.
Compactions are ongoing. So what I basically do is start and get a reference to the files. Open the files so that I can read them. So there's some sort of race conditions where stuff may or may not exist. So if I get an error, I retry. So yeah, so when there's ongoing compactions, you will find some stuff gets deleted. But I think I've worked around that, so it works.
And also, you said Hive on Cassandra is quite bad compared with Shark. If you compare Hive versus Shark, or is Hive is completely bad, so it's not comparable?
Yeah, I didn't run Hive, so I guess the first stage of Hive would be to read through all the data, which would be fairly similar. I mean, the reason why Shark is better is because we're not writing stuff out to HDFS. So I didn't have. If I'd done that, then I would have had data nodes running on my Cassandra cluster as well, and loads of other stuff. Or maybe I had a separate HDFS cluster. I don't know, but that would have involved more stuff, so it would have been worse. Yep.
So your result set is on one node of the cluster, effectively, is it?
No, it's distributed in memory.
It is distributed in memory, right, across the cluster.
Yes.
So when you run that second query and it took 18 seconds, it was actually interrogating memory structures across.
Yes. Yes. So for my case with 60 megs of RAM, that doesn't really matter, but it means that you can, I had 1 gig of memory allocated, so I could actually have cached 4 gigs of data and run it very quickly on
Run
that.
multiple queries at the same time?
You could, but you would have to set up Mesos or Yarn to be able to do that, and then it would schedule between them. Jonathan?
So the storage handler, is this a Hive-level storage handler or a Spark-level storage handler?
It's a Hive one, but they're the same thing. So Shark can use all Hive storage handlers. So the CQL storage handler I'm using is just the bog standard CQL storage handler that I downloaded from whatever GitHub project it's on.
So with Hadoop, you can send a map job to a node that doesn't have the data locally. It will go fetch it from another one. And so for this one, it sounds like you're basically saying it must have the data locally because I'm going to read the SS tables directly.
Yes.
So is that a difference between Spark and Hadoop there, then that Spark will always do local reads, or is that?
I'm not sure. I certainly it prefers to do local reads like Hadoop does. I'm not sure if you can say only do local reads. I mean, in my case, if you try and do a non-local read, it will throw an exception and say can't do it. So I'm not sure if you can force Spark to say, look, you've just got to wait until a node with the data is up or free. Yep.
So does Spark have its own implementation of the Hadoop file system?
No.
Or does it?
But you can, So Shark can read out of HDFS. So if you'd have normal HDFS, you know, Hadoop data nodes and whatever.
On top of Cassandra, not as a separate node.
No, that's totally separate HDFS. Standard HDFS you can run, and Shark can load from that. I mean, I suppose.
Spark itself, does it run on top of Cassandra?
In my case, Spark is running. Well, Spark is just the processing, but yeah, it's pulling data out of Cassandra or the SS tables. Any more questions? All right, thanks very much.